Hello, everyone. In this class, we will learn about the construction and acceptance of bioretention facilities. From our previous lessons, we know that bioretention facilities refer to areas in lower terrain where plants, soil, and microbial systems are used to infiltrate and purify runoff rainwater. They are divided into simple bioretention facilities and complex bioretention facilities. Depending on their application location, bioretention facilities are also known as rain gardens, bioretention strips, elevated planters, eco-tree pits, etc. Bioretention facilities are mainly used around buildings in residential areas, roads, parking lots, and urban green spaces. They are also found in urban road green belts. The structure of bioretention facilities from top to bottom typically includes an overflow layer, water storage layer, cover layer, filter layer, transition layer, and drainage layer, among others. Therefore, the outside and bottom of bioretention structures should be lined with permeable geotextile fabric to prevent surrounding soil intrusion. If the permeable surface at the bottom of a bioretention facility is less than 1 meter above the seasonal high groundwater level, or if the facility is less than 3 meters horizontally from the building foundation, or if the facility is located within a road green belt and close to the roadbed, a waterproof layer needs to be installed. Additionally, bioretention facilities also include inlet pipes overflow valves, drainage blind pipes, and inspection ports. For areas with severe runoff pollution, pre-treatment facilities are also necessary. Now, let's proceed to learn about the general regulations for the construction of bioretention facilities. Using complex bioretention facilities as an example. First, before construction, the relevant drawings and documents should be reviewed to identify any buried underground utilities or hidden obstacles in the designated area. This is to avoid damaging the utilities or disturbing hidden obstacles during construction. Before construction, the infiltration capacity of the surface soil in the infiltration area and the groundwater level should also be recorded. Second, before excavation, filling, and compaction, a site survey should be conducted to select the construction method. An engineering plan and safety protocol should be prepared. The construction process should not reduce the natural soil's infiltration capacity. Third, all raw materials, semi-finished products, and other items used in construction should be inspected and approved before entering the construction site according to relevant requirements. The construction of bioretention facilities should comply with design specification. For complex bioretention facilities, from top to bottom, the requirements for each layer should meet the following conditions. For example, the water storage layer should have a thickness or depth of 200 to 300 on. Additionally, an overflow of 100 millimeters should be provided. The cover layer is usually covered with dry leaves or bark. Its maximum thickness should be 50 to 100 millimeters. The vegetation and planting layer should generally use sandy soil with a high permeability coefficient. The sand content should be about 60% to 85%. The organic content should be around 5% to 10%. The clay content should generally not exceed 5%. The thickness of the planting soil layer depends on the type of plants used. When using herbaceous plants, the thickness is usually around 250 millimeters. If there are no design requirements for the replacement layer, a permeable geotextile fabric should be installed. The planting layer and the replacement layer, or a sand filter layer with a thickness of 50 to 100 millimeters. The replacement layer should include perforated drainage pipes with a thickness of 300 to 600 millimeters. Next, let's learn about The construction process of bioretention facilities. The construction process for bioretention facilities should be determined based on the structure of the facility, the site conditions, and other factors. The general steps are as follows. First, construction preparation and line measurement. Then, earthwork construction, overflow facilities installation, waterproof layer installation, drainage layer installation, transition layer installation, replacement soil layer installation, landscaping, cover layer installation, and the installation of other auxiliary facilities. First, let's look at line measurement. The construction team should follow the overall project site plan or the site coordinates provided by the construction company to establish control points and elevation benchmarks. A construction measurement control network should be established. The horizontal control network can be established using a building grid survey, satellite positioning survey, triangulation network survey, traverse survey, etc. If there is already an established elevation control network in the survey area, the existing elevation system can be used. Bioretention facilities should be located at the lowest point of the catchment area. During construction, attention should be paid to the site and the vertical connection with the bioretention facilities. The excavation depth of the bioretention facilities should be calculated according to the construction drawings and design documents, considering the site's vertical alignment. The elevation of the pit bottom should be checked, along with the final surface elevation and the overflow inlet elevation. It should be ensured that the facility can vertically connect with roads, paving, green spaces, and pipelines within the catchment area. During the layout process, the horizontal position error should not exceed 50 mm, and the elevation error should not exceed 5 mm. After construction is completed, the same method used for layout should be applied to measure and verify the facility's horizontal and vertical positions. At this point, the horizontal position deviation should not exceed 100 mm, and the elevation deviation should not exceed 10 mm. The layout of bioretention facilities should verify and avoid existing or planned pipelines to prevent gas and power lines from crossing the facility. This is to prevent pipeline damage during excavation. For earthwork construction, during pit excavation, the construction finished surface of the bioretention facility should be used as the reference. Excavation can be carried out using a combination of mechanical and manual methods. Manual trimming can be used to connect with surrounding green spaces. Soil should not be randomly discarded when excavating a pit above an underground space's roof. The structure of the roof should not be damaged. After the pit excavation for the bioretention facility is completed, the excavated soil should be promptly cleaned up to prevent soil collapse, which could negatively affect the depth and performance of the bioretention facility. When the soil cannot be cleared in time, temporary dikes should be set up around the bioretention facility. And at the reserve water inlet, temporary dikes should be installed to prevent soil erosion, as shown in the following diagram. From top to bottom, there are the top line, which is the connection line with the side line 1, the finish line, which is line R, and the excavation bottom line, which is line Z, to ensure the accuracy of the excavation slope. The bottom line, line 3, and the finish line, line 2, should be marked during layout. Let's review the earthwork construction. The bottom soil of the bioretention facility should be compacted according to design requirements. After compaction, the depth should be measured to ensure it meets the requirements for the drainage layer, transition layer, replacement soil layer, retention height, overflow height, and surrounding catchment. The pit bottom and floor should be level, compact, free of loose soil, and without significant bumps. There should be no stones, bricks, tree roots. Width silt, or other debris, rainwater should be promptly removed. A natural gentle slope should be used to address the connection between the bioretention facility and the surrounding site if site conditions are restricted. A vertical wall bioretention facility can be used, as shown in the diagram. This mainly includes steel plates, gabions, wooden piles, grass stone separators, concrete retaining walls, etc. Next, let's learn the construction of the inlet and overflow structures. The elevation of the bioretention facility's inlet should be 30 to 50 millimeters lower than the surrounding catchment area to facilitate rainwater inflow. In areas prone to erosion and sedimentation, the bioretention facility should have anti-erosion and filtration facilities installed at the inlet. For example, 20 to 30 millimeters diameter gravel or crushed stone can be laid as a cushion with a thickness of not less than 50 millimeters. The width of the gravel bed should not be less than the width of the inlet. Overflow facilities are a crucial part of bioretention facilities. They transport stormwater through overflow wells to the municipal drainage system, ensuring the proper functioning of the bioretention facility. Reinforced concrete masonry, concrete block assemblies, or brick-built overflow wells can be used to comply with the Code for Construction and Acceptance of Water Supply and Drainage Pipeline Engineering. Request to expand. When the overflow meets design requirements, a vertical pipe can be used instead of an overflow well. The overflow well should be checked against the facility's inlet for horizontal positioning. The overflow outlet should not be located near the inlet, as shown in the diagram. The drainage blind pipe and the outlet pipe of the overflow facility should be connected using a level or water level joint. This ensures smooth drainage. The overflow facility cover can be trapezoidal or dome-shaped. It should meet the rainfall discharge requirements for the catchment area within the design, and it should also have anti-clogging features. Next, let's look at the construction of the waterproof layer. The choice of waterproof materials should meet design requirements. If the design is unclear, high-density polyethylene HDPE membranes or non-woven geotextiles can be used. The HDPE membrane thickness should not be less than 0.5 millimeters, and the non-woven geotextiles weight should not be less than 600 grams per square meter. The water pressure test should be conducted at 0.3 MPa for 30 minutes without leakage. The waterproof material should be free from damage, wrinkles, or unjoined sections. The bottom of the waterproof material should not have any stones, soil blocks, or other hard objects protruding. The top of the slope with the waterproof material should be anchored. The waterproof material should be buried in the anchor trench, with the trench depth no less than 300 millimeters. For the splicing method of waterproofing materials, weld and wall seam joining can be used. HDPE membranes should be heat welded, with a joint width of no less than 100 millimeters. Non-woven geotextiles should be double-stitched, with a joint width of no less than 75 millimeters. The direction of laying the waterproof material should be carefully chosen to minimize stress on the joints. It should be laid from top to bottom in one go, with enough slack to accommodate thermal expansion contraction, soil medium, and backfill-induced stretching. The laying direction of the waterproof material on the slope should be consistent with the slope. It is best to lay the entire roll on the slope. Horizontal joint should be avoided. Next, let's look at the construction of the drainage layer. The drainage layer functions to remove excess rainwater. The drainage layer can be made of gravel or crushed stone. The particle size of the crushed stone should be uniform, typically 10 to 20 millimeters in diameter. The smallest particle size should not be smaller than the drainage blind pipe's perforation diameter. The crushed stone should not leak from or clog the drainage blind pipe. Or clog the drainage blind pipe. Before laying, the crushed stone should be washed. To prevent secondary pollution and clogging of the drainage blind pipe, the wash water should not be directly discharged into the rainwater drainage system. The drainage layer should be laid in layers, with a thickness of 200 to 300 millimeters. Laying should be done into steps. First, when the thickness of the crushed stone reaches 50 to 100 long, it should be compacted, leveled, and sloped. While installing the drainage blind pipe and inspection pipe, second, continue to lay the crushed stone until it reaches the designed depth, completely covering the drainage blind pipe. For drainage blind pipes, PVC, UPVC, PA, PPR, or HDPE double-wall corrugated pipes can be used. Flexible permeable pipes should not be used. The ring stiffness of the pipe should not be less than 4 kilonewtons per square meter. The wall thickness of the blind pipe should meet the relevant standard requirements. The perforation rate of the drainage blind pipe should be controlled between 1% and 3%. The diameter of the perforations should be controlled between 4 and 8 on. The spacing of the perforations should be uniform. When laying the drainage blind pipe, it is advisable to use a grid pattern. The spacing of the blind pipes should be properly determined to meet the water collection capacity requirements. The main pipe diameter of the drainage blind pipe should not be less than DN 150 millimeters, and the branch pipe diameter should not be less than DN 100 millimeters. The slope of the drainage blind pipe should not be less than 5. The slope can be adjusted using wooden wedges. To ensure proper drainage slope, bioretention facilities should have inspection vertical pipes connected to the drainage blind pipe. The inspection vertical pipes should be made of UV-resistant materials that are also resistant to thermal and oxidative aging. PVC, UPVC, HE, or similar materials can be used. The pipe diameter should match the main drainage blind pipe's diameter, or be one size larger. Next, let's look at the construction of the transition layer. Bioretention facilities should have a transition layer to prevent the planting medium or replacement soil layer from invading the drainage layer. The materials for the transition layer should meet design requirements. If the design is unclear, sand and gravel can be used. If sand and gravel are used as the transition layer, they should be washed before laying to prevent secondary pollution and clogging of the drainage blind pipe. The thickness of the sand and gravel transition should not be less than 100 millimeters. It should be evenly laid. Manual or small machinery can be used. For light compaction, compaction should not damage the drainage blind pipe. Next, let's look at the construction of the replacement soil layer. The replacement soil layer can improve soil permeability. The replacement soil layer should meet the requirements for rainwater infiltration and plant growth. Its thickness should not be less than 300 millimeters. The saturated permeability coefficient of the replacement soil layer should be between 1 times 10 to the power of minus 5 meter per second and 5 times 10 to the power of minus 5 meter per second. If these conditions are not met, soil replacement should be carried out. The replacement soil layer should not use clay or sand directly for backfilling. This prevents compaction, stratification, and clogging. The organic content in the replacement soil layer should meet the needs of plant growth and comply with relevant standards such as the greening planting soil. The replacement soil layer should be backfilled in layers, with each layer being 100 to 200 millimeters thick. Manual or small machinery should be used for light compaction. During compaction, the transition layer and drainage blind pipe should not be damaged. After the first backfill is completed, the final surface elevation should be slightly higher than the design elevation. Subsequently, 2 to 3 passes of watertight compaction should be carried out until the elevation reaches the design final surface elevation. The double ring method can be used to test the saturated permeability coefficient of the bioretention facility and ensure it meets the requirements of relevant standards, such as the standard test methods for geosynthetics. If the permeability coefficient is too large or too small, the ratio of the replacement soil layer medium should be optimized to meet the permeability coefficient requirements, ensuring no water leakage or clogging. This will ensure that the permeability coefficient meets the required standards. Next, let's look at the construction of the cover layer. The cover layer can effectively reduce the blockage of the planting soil layer by suspended solids in rainwater runoff and prevent surface soil compaction, which can reduce the infiltration performance of the retention facility. Therefore, carbonized bark will crush stone with relatively high density and with certain water retention, and pollutant absorption functions can be used as the cover layer. The thickness of the cover layer should be around 50 millimeters. It should be washed before laying. The cover layer material should be evenly laid to ensure no soil is exposed. For the landscaping project, the planting in the bioretention facility differs from regular landscaping. It is recommended to use full-grown plants with high specification, and excessive pruning should be avoided. The planting density should be appropriately increased by about 20% over the conventional density. To ensure no soil is exposed, it is advisable to enrich the variety of plants and use group planting to avoid a scattered appearance inside the facility. For example, a combination of cluster planting, mass planting, group planting, and solitary planting can be used for the layout, a combination of density and openness. This approach balances aesthetics and function. After summer planting, daily watering is necessary to ensure plant survival. We have now covered the general construction methods and the main construction methods for bioretention facilities. Next, let's study the acceptance of bioretention facilities. The acceptance of bioretention facility projects should be organized by the construction unit involving the design, construction, supervision, and related units. The project should be checked for completeness, and the associated facility should be reasonably arranged. Acceptance can be carried out using a comprehensive evaluation method. Following the standards for construction and quality acceptance of sponge city infrastructure, the acceptance items are generally divided into main control items and general items. First, let's look at the main control items. The structure of bioretention facilities should meet design requirements and should not cause secondary disasters such as subsidence of surrounding buildings or roadbeds. The inspection method is visual inspection and steel tape measurement. The overflow inlet of the bioretention facility should meet design requirements. If there are no design requirements, the overflow inlet should be 100 mm lower than the surrounding ground level, and 100 mm higher than the top of the design water storage layer. The inspection method is visual inspection and steel tape measurement. The depth of the water storage layer, the thickness of the replacement layer, and the materials used should meet actual requirements. The inspection method is visual inspection and steel tape measurement. The thickness and main components of the planting layer should meet design requirements. The inspection method is to review the test report and conduct steel tape measurement. The drainage time of the water storage layer should meet design requirements. The inspection method is by water filling experiment, or by observing and timing actual rainfall. The general acceptance items for bioretention facilities include the specification for permeable geotextile isolation layers should meet design requirements. If the design is unclear, the unit mass should be 200 to 300 grams per square meter, and the geotextile overlap weight should not be less than 150 millimeters. The inspection method is to review the geotextile certificate of conformity and to conduct steel tape measurement. The gravel drainage layer's particle size will meet design requirements. If the design is unclear, the particle size should be 25 to 40 millimeters. The inspection method is visual inspection and caliper measurement. Isolation layers generally use sand. The thickness of that sand layer, with a thickness tolerance of plus or minus 10 millimeters. The inspection method is visual inspection and caliper measurement. For perforated drainage pipes, the surface should be smooth, without bubbles or cracks. The pipe diameter and strength should meet design requirements. The inspection method is to review the certificate of conformity and quality inspection report. Check the product's acceptance records upon entry to the site. The bioretention facility shape can be adapted to the terrain, but the area and volume should not be less than the design requirements. The inspection method is visual inspection and steel tape measurement. Alright, in this lesson, we learned the general regulations for the construction of bioretention facilities, the construction process, the main construction methods and key considerations. The acceptance items for bioretention facilities are mainly divided into main control items and general items. We have provided the inspection methods. Alright, that's all for this lesson. Goodbye, everyone.